target is I can define the atomic radius and determine relative size of atoms from the periodic table. So first of all, what is the atomic radius? That's, of course, the radius of the atom. It's the distance from the nucleus to the outermost energy level, and it tells us the size of the atom. So a trend in the periodic table is a general pattern that the elements follow. So the atomic radius, as we move down from top to bottom down the periodic table, is going to increase because each time you move down a row, you add an energy level. So the size of the atom is going to increase. Now as you go across from left to right, it's going to decrease because you're adding protons, you're not adding any energy levels, and the attraction of the nucleus for the electrons increases. So that pulls the electrons in closer. So what that looks like is this. So atomic radius increases as we go down and from right to left. So your largest atoms are down here in the bottom left. So the smallest would be up here in the upper right. I can define ionic radius and determine the relative size of ions. Now this is a little bit simpler. The ionic radii, remember that an ion is a charged particle, and a cation, which is our positive ion, is going to be smaller than the atom that it came from because it has lost an electron. And this happens in the metals. Anions are negative ions. They're larger than their atoms because they gain electrons, they gain negative charge. And this happens in the nonmetals. I can define ionization energy and arrange elements in order of increasing or decreasing ionization energy. The ionization energy is, remember that an ion is a charged particle, means it has a different number of electrons. So the ionization energy is the energy needed to remove an electron from an atom, to take away an electron. Metals are going to lose an electron very easily. That's what they like to do to form ions. So they're going to have lower ionization energy. So the more metallic character an ion has, the lower the ionization energy is going to be. It's going to decrease from top to bottom, and it's going to increase from left to right. Now there's a few reasons for this. The nuclear charge is going to increase as we go left to right, so the ionization energy is going to increase. The shielding effect. This is where you've got lots of electrons between the nucleus and the outer electrons, kind of like when you guys like to sit in the back of the classroom if you had your choice. The radius increases, you have less ionization energy. The electrons get further and further away, so there's weaker and weaker attraction. And the sublevels, if they're full or half-full sublevels, they're going to require more energy because they're more stable. So what this looks like here, here's ionization energy. It increases as we go to the right, and it increases as we go up. So over here in the upper right is your highest ionization energy. These guys hang on to those electrons more than any other atom. So helium would have one of the highest ionization energies. Electronegativity. Here's our learning target for that. So the electronegativity is the shared attraction for electrons in a molecule. Now it's going to follow the same trend as ionization energy for the same reasons that ionization energy decreases top to bottom and increases left to right. So you'll notice on our periodic table that electronegativity follows the same pattern. So the highest electronegativity is here. Actually, fluorine has the highest electronegativity of any atom. Electron affinity, we're going to describe the relationship between electron affinity and metallic character. So electron affinity is the energy related to the loss or gain of an electron. The more metallic character an atom has, the lower the electron affinity, sorry. So as the metallic character increases, electron affinity is going to decrease. So if we look at our periodic table, here's metallic character. We'll talk about that in just a minute. Metallic character increases the closer we get to the bottom left. So electron affinity, notice, is increasing up in the top right. Alright, so as non-metallic character increases, so is electron affinity. Let's describe the relative reactivity of metals and nonmetals. Here is reactivity man. Now, this is the back of his head. He's looking at the periodic table. His left hand is pointed down. His right hand is pointed up. So, at the bottom of his left hand is going to be the most active metal. And his fingers over here are pointing to the most active nonmetal. So if we're looking at the periodic table, bottom left-hand corner, the most active metal is going to be francium. So up here, the most active nonmetal is, if you're looking at the periodic table, you might be tempted to say helium. But remember, helium is a noble gas and it does not react. So the most active nonmetal is actually fluorine. Alright, to summarize, here's our periodic table again. So metallic character is greatest in the bottom left-hand corner. This is where reactivity man is pointing to with reactivity. Non-metallic character increases as we go up and to the right, which is where ionization energy, electronegativity, and electron affinity are at their greatest. Here is a table that summarizes everything. If you'd like to pause the video and jot this down. Atomic radius is going to decrease left to right, increase from the top down. Your cations are your positive ions, so they're smaller than their atom. Anions are negative, so they're larger. Ionization energy and electronegativity increase left to right, decrease top down. Electron affinity, the more metallic character, the less electron affinity. Your metallic character is going to follow that same trend. It decreases as you go top to bottom, decreases left to right, increases top to bottom. And reactivity for metals, the more metallic character, the more reactive your atom is. For nonmetals, the more nonmetallic character there is, the more reactivity there is.